So, can someone tell me what 0.1 plus 0.2 is?
It's a trick question.
No. Best guess. Yeah, you. Yeah, very nice. It's very easy, right? However, if you ask a computer this question, it might not be so easy for it. So a computer might give you 0.3, a whole bunch of zeros, and then a 1. It's not so easy for them. I mean, you might think they're super smart. How come they can't actually answer this question accurately? But the reason computers make this dumb mistake is because they actually follow the floating point number system. And floating point numbers make big numbers small so that computers can actually calculate things faster. And floating point calculations is all about quickness and efficiency, right? So much like what we do in real life, right? You wouldn't go around telling someone, hey, I saw 3,150,062 ants at the beach, right? You would seem like a nerd, right? You wouldn't say that. So you would actually say, hey, I saw like 3 million ants on the beach today. So computers also shorten these numbers to save time. So to understand how computers do this, we must first understand how we deal with numbers, right? So we have 10 fingers, right? And we use 10 symbols to represent these 10 fingers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we also have places to put these numbers on. We have the hundreds place, the tens place, ones place, and we also have places for fractions, like 10 and million and thousand. So for example, if we want to represent this number, 45.6, well, it has 4 tens, 5 ones, and 6 tens, because it is 3 plus 5 plus 6 over 10. So we represent it as this, 45.6. And we can save time using scientific notation, which is something you might have heard of before. And it's fine if you don't. So, for example, can someone tell me right off the bat what 3 million times 15 million is? Yeah, it's not so easy to do, right? So with scientific notation, it can be like super easy. All you have to know for scientific notation is that we want the important number and we want a power of 10, which is just how many times are we multiplying by 10. So in this case, in 3 million, we have the important number, which is 3. And to get to 3, we need to jump 8 zeros. So 3 million would be 3 times 10 to the 8. Likewise, for 15 million, the important numbers are 1.5. And to get to the first important number, we need to jump 7 spaces to the right. And if we're jumping to the right, we count negative. So thus, 15 million would be 1.5 times 10 to the negative 7. And now all we need to do to calculate this multiplication would be to just multiply the important numbers with important numbers and the powers of 10 with the powers of 10. So 3.3 times 1.5 would just be 4.5, and then 10 to the power of 8 times 10 to the power of negative 7 is 10 to the 1. And a trick is to just add the numbers at the top, and you get the multiplication. So we get 4.5 times 10, which is 45. And this is really cool because we don't have to depend on the long multiplication, right? With all those zeros you get at the end. No, you just use scientific notation and you get the answer pretty quickly. So how do computers deal with numbers then? Computers don't really have fingers, right? But actually, they kind of do. So internally, computers have states, off and on. And these can be sort of treated like fingers, right? So 2 fingers, 2 symbols, and 2 numbers to represent them, 0 and 1. And so they also have places. But instead of the decimal system, which we use powers of 10, we use the binary system, which uses powers of 2. So powers of 2 are like 8, 4, 2, a half, 1/4, and so forth. Because 8 is 2 to the power of 3, 4 is 2 to the power of 2, 4th is 2 to the negative 2, so forth. So for example, 9.25 has 1/8, 0/4, 0/2, 1/1, 0.5, and 1/4. Thus, 9.25 is 1001.01 in binary. Let's break that down a little bit more. So we know that 9.25 is 8 plus 1 plus 0.25. We know that 8 is 2 to the 3, 1 is 2 to the 0, and 0.25, which is 1/4, is 2 to the negative 2. Thus, 9.25 equals 1 times 2 to the 3, 0 times 2 to the 2, 0 times 2 to the 1 times 2 to the 0, 0 times 2 to the negative 1, and 1 times 2 to the negative 2. Thus, we have 1001.101 in binary. But here's the problem. Some numbers that are easy for us are really hard for computers to understand. For example, 0.1, which is a super easy number, can be really hard for a computer because 0.1 in binary is 0.001, 00011, 0011, 0011, 0011, and so on and so forth for infinity. Which is okay if you had infinite storage, but actually we don't. Computers, you might have heard, are 32-bit or 64-bit. And this is basically how much paper you have for a computer to write all its numbers. And since it has a finite amount of paper, it has a finite amount of space, and it can't really store numbers like infinitely long, right? So for example, 0.1 would actually be this number, and it doesn't go on for infinity. And if we translate this number back into decimal, we actually get this number, which, as you can see, is not quite equal to 0.1. Another example is 1/3. 1/3 is a third. And we know if we add a third plus a third plus a third, we get 3/3, which equals to 1, right? But for a computer, actually, 1/3 is 0.333333 until you get to the 3. And at that 3, you can no longer write any more 3s, so it actually just stays that way. So when you add a third plus a third plus a third on a computer, you actually get 0.999999 until you can no longer store any more 9s. And that clearly is then equal to 1. So these kinds of errors are called floating point rounding errors. They happen because computers can't store enough digits, so they actually just shorten numbers instead. And you might think, wow, this is a huge problem. Well, it isn't. Say if I want to calculate the distance from here to Killing Hall, you really wouldn't care if you're off by an atom of a distance, right? So humans really don't need infinite precision. They just need approximations. And approximations are perfectly fine for us.